Also, I graded your exams last night. If you have any objections to any of the grading I did, just let me know. The primary thing that I noted for the exam was I think only one person got the analysis question right on what happens with the tree. So let's go over that first. Okay? So the question is, we've got a tree here, right? Sorry, we've got a tree here. With 3 branches. Also worth noting that the structure itself is recursive. Okay? Because they could have weird rules where it's not recursive, or, And the question was, how does having 3 affect having 2? Now, most people were correct, and they put it's 3 branches, so the runtime is going to be log of 3n. Some people were even further correct, and they said, and that's the same runtime, which in terms of big O analysis, that is technically correct, which is the best kind of correct. Futurama reference, so I guess not. All right, regardless of my dated TV references. However, that being said, I've had people say that the general thing that got people only 3 points was people saying log 3 of n is slower than log base 2 of n, and that is false. Log 3 is faster. Log base 3 is faster. Now, some of you argued that it should go slower because there are more comparisons, and it is true that there are more comparisons. However, your overall tree path is going to be shorter, because what you're doing is that when you are in a binary tree, right, if it's balanced, then if we go left or right, we are discarding half of the choices. But in here, if we go left, right, or center, we are discarding 2/3 of the choices. So we shrink it, so it gets shrunken to 1/3 each step of the way, which is why it gets faster. So I did give points though for like people's logic and reasoning, because in this kind of class, I do try to make sure you get credit for actually using your brains, even if it brings you to the wrong conclusion. Unfortunately, humans work off of faulty, unambiguous instructions, and some of your logic is true. Like, yes, more comparisons means more comparisons, which means more checks. It just doesn't add up in the same way as you'll eventually see if you take 3223. Now, over here in my GitHub page, which is linked to from the front page of Canvas, okay, if we look at the destruct folder on my GitHub, there's something here I have called Study Guide. And for my final exams, I'm usually very lazy, and I don't actually practice final exams because there's just so many good questions out there that but there's only so many that are really useful for me to ask on my exam. So instead, what I prefer to do is go over other people's final exams. So before we do that, though, I simply have a write-up of all of these topics that we've went over in the class, which is actually a lot for 8 weeks. We went over big O notation, right? And you will more formally cover big O notation in 3223, okay? If you haven't already. But we've got a good feeling as to how 5 different important polynomial times work. We've got constant time, logarithmic, linear, log linear, and n squared. All of which are actually technically efficient runtimes. N squared does, in comparison, especially with the restriction I've been putting on you, n squared we've been probably led to believe isn't that efficient. But the definition of efficient algorithms that's used in computer science is if it's not exponential, it's efficient. On a technical sense. Sorting out algorithms. My videos went over a bunch of sorting algorithms, and there are tons and tons and tons of sorting algorithms. But the three that you care about for the exam is, first off, insertion. Why do I care about insertion sort? Insertion sort has a lot of special properties. It's by far my favorite sorting algorithm because it shows that even something with a not great runtime of n squared is still actually can be great under the right circumstances. You can simply optimize it for very small data sets. So first off, it's by far the best for doing O of n squared. It's of the O of n squared, it does the least amount of comparisons. So it's more efficient in practice than selection sort or bubble sort. So even though they have the same runtime, big O time, it does run faster. It's adaptive. That's the big thing. So it works extremely well for things that are almost completely sorted. If things are almost completely sorted, then great. If there's only one thing out of place, this will run in O of n time. If it's already sorted, it'll run in O of n time. We'll go over that a bit. Stable, it doesn't change. If this happens matters for sorting objects. If you've got a 5 and then another 5, if you've got like two 5s, it will ensure that the first 5 comes first and the second 5 comes after, even though those 5s are completely fungible. But if you're dealing with objects, your objects may not be fungible. And finally, it's online, which means that you can take your sorted, you can work on sorting your data as you're receiving it. Meaning you may not get all, if you're busy sorting like a bunch of papers and then somebody dumps in more papers on your desk, you don't have to start over. A bunch of other algorithms you're going to need to start over. So we care about it for those reasons. Quicksort and partition. Quicksort we care about because even though it's O of n squared worst case, we generally look at it as an n log n algorithm. Know why we care about it being the rationale for it being n log n. Also, partition. Know how to do partition. On my exam, I generally ask you to do on my exam, and I'm going to go over this because I didn't talk about this in my actual, we didn't do the sorting assignment in class. So in my exam, I generally ask you, okay, and I'm just going to make something up. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we've got an odd number of items. Saying using the leftmost item or the item at the first index as the pivot. This is the way the question is phrased. Oh, come on. Using the leftmost item as the pivot. Please select which of the following is the state of the array after the partition algorithm is executed on it. So in other words, and what does partition do? It divides it into everything less than the pivot, the pivot, and everything greater than the pivot. Now, the wrong answer for this, okay, this is the wrong answer. Come on. Why do you do this to me? Why do you do this to me? Because, there we go. Okay, the wrong answer for this is as follows. 5, 6, 8, 3, 1, 4, 7, 2, 9. That is the wrong answer. Where we just because while you have partitioned it, that is not the way the partition algorithm works. Because the partition algorithm has a very specific way of doing it in place. Make sense? Because, this technique, 1, 2, 4, 3, 5, also valid partitioning. But that's not how the partition algorithm works in practice. It has to do it in place. So how does it work? We create two variables, up and down. We move up the array, looking for the first item it finds that is bigger, and move down the array, looking for the first item that's smaller. Okay, so let's go ahead, move up the array, up. We're going to move down to the first item that is down to the first item that is smaller. Right? Okay, we found them. So in the next step now that we found things that are bigger and smaller than the pivot, we swap them. So 2 and 6. And now we continue. Move up for the first thing that is bigger, and down for the first thing that is smaller. And now swap them. 4, 8. There we go. Now, the last step, notice that, now we look up for the first thing that's bigger, down for the first thing that's smaller. Once they've crossed, we know that we're done, right? We now have down, below, up. So they've crossed, so now we know that we're done. Now what do we do? So currently it's partitioned into these three categories. Pivot, less than pivot, greater than pivot. And to get the correct answer, what we do is we now take the pivot and swap it with where down was. And so the answer, it was 1, 2, 4, 3, 5, 8, 7, 6, 9. So that is one iteration to partition, and then what will happen next in the algorithm is that we recursively call quicksort on those things. Okay? So merge sort also exists. That's one thing I want you to know more theoretically. Also, what is the disadvantage of using merge sort? Since it always runs in n log n time, can anybody think of a disadvantage of merge sort? Let's go ahead. It always runs in n log n time. So let's go ahead and take a look at merge sort. Just straight up merge sort and quicksort. Merge sort, worst case, best case, average case is always n log n. Worst case is that it uses O of n auxiliary space complexity, unless you're explicitly writing it to work only with linked lists. Linked lists you can move around with constant time, it uses constant space. But if you're making it in general, and we always think about these using on arrays or array lists in general, then it works, then it needs extra space. Quicksort, if it's implemented, as long as we're doing it correctly, log n, it uses less space because it can be done in place. And where does this log n come from? From the recursive calls, which merge sort is going to have anyway. So it's clearly beating merge sort here. Okay. So merge sort has that disadvantage of that. Huffman encoding, right? For the exam, you're not going to write any data structures, but you need to know how to write code that uses them. You don't actually, I'm not going to say build a tree or build a sorted linked list or something like that. I'm going to say, okay, use this to do that. We'll see in a minute what kind of tasks I'm doing. But we care about lists, stacks, queues, trees. In theory, about the heap, you're not hash tables and graphs. Know your representations of a graph, and how to get from like a drawing to a matrix or a list, or from a matrix or a list to a drawing. We'll go over that today. So some finals from other institutions, and most of these are now dead because I wrote this like 6 years ago. Let's see, yeah. So I'm going to start off where we are. Let's keep going on sorting. Problem 2, so part of the issue is that if you look for practice data structure finals, by the way, you'll find that that you're like, okay, some of these questions I understand, but some of these questions I don't even have a clue. Did I mess up in data structures? And the answer is no. it's just the way the computer science curriculum works. The question is, where do we divide the courses up into content? Because at Temple we do Intro to CS, Object-Oriented Programming, Data Structures, Algorithms. This is the core CS computer science curriculum that every school has to do, but we also used to do it as Intro and Object-Oriented Programming, Data Structures, and Algorithms. So we used to do it as 3 classes. So you can see, you can spread it among 2 classes, you can spread it among 3 classes, or 4 classes, depending on how you want to do it. And then also, where do you want to draw those dividing lines? So consider insertion sort versus merge sort. For each algorithm, what is the worst case asymptotic upper bound on each running time if you know additionally that the input is sorted, the input is reversely sorted, it contains n copies of the same number. So we're going to go over insertion sort first. Okay, an asymptotic upper bound, worst case, that means what's the big O worst case? Okay, and it's generally asking for a tight asymptotic upper bound, because if it's just an asymptotic upper bound, technically I could write like 2 to the n and technically be correct, but that's not useful. Okay, so if the input is already sorted, if the input is already sorted for insertion sort just checks everything, sees there's nothing to move down, and it ends, so it takes O of n time. It's best case scenario, actually, for insertion sort, that everything is given to it sorted. If it's reversely sorted, that's actually insertion sort's worst case scenario, because you've got you take your first item and you go, that's great. Second item, you have to swap it once. Third item, you have to swap it twice. Fourth item, you have to swap it 3 times. And so on, so it's 1 plus 2 plus 3 plus 4 plus 5. It's all the way up to n squared. So that is explicitly, for this one, O of n squared. Input is a list containing n copies of the same number. If you think about that for a second, that's technically sorted. So that's the best case scenario. If we're just sorting numbers, all numbers are the same, there's nothing to move, so we're all good. Or you could argue it depends on the implementation of insertion sort, but we're going to assume that it's programmed the way we really would like it to. Merge sort. A, B, and C all have the same answer, n log n. It doesn't matter. Merge sort always works the same way. It always breaks everything up and combines it. It has, basically, you have log n layers with each layer taking O of n time. It always works that way. Doesn't matter if it's reversely sorted, already sorted, or if it's all the same numbers. Make sense? Okay. I'm actually going to open up Edge for a second, because on Edge, I should be able to draw on it. Okay. All right. So let's see. Okay. So this is one that's good for hash tables. We know that hash tables are common in practice and when you have a lot of insertions, deletions, and search operations. We've seen under the assumption of uniform hashing, collision resolution by chaining, and a constant time computable hash function, and deletion search are both plus 1 plus n divided by m worst case. Okay. So we can see that this can be divided, reduced to constant time under one additional assumption. That is where basically we keep everything to be the same size into a constant factor, and when it gets too big, we simply refactor. This is the more important one. Suppose we have a hash table and have inserted some elements. When you inspect it, you see that the result looks like the picture below. Being a good student, you realize that this is a problem. What is the problem here? What is the problem with this hash table? Give you a second to think about it. Now, the issue with the hash table is that with hashed functions, just to review, because we've been going through this at a whirlwind pace, is that we want things to be uniformly distributed, or close to uniformly distributed as possible, meaning we want a lack of collisions. And here, pretty much every space has a collision. Pretty much this is using hashing by chaining, so every space is a linked list. And we see that we have a lot of empty spaces. In fact, if we count them up, more than half of them are empty. And so we have a lot of unused spaces. That means the hashing function is bad, because the hashing function is sending things to the same key. It's sending things to the same key too easily. I mean, because your universe of keys is bigger than 20 different keys. But here we're in a bit of an issue. So what is a hash function that could give rise to this behavior? Okay? So we got to figure out something common with all of these elements. And let's think, and just to give you a hint, if we look at the ones place for all the digits, everything with the same ones place ends up in the same key. Sorry, ends up in the same slot. So see all the zeros, they ended up in 0, all the 1s in 2, all the 2s in 4, all the 3s in 6s, all the 5s in 10s, all the 6s in index 12. So that gives us, and when we say it out loud like that, that gives actually a pretty good relationship, right? 0 to 0, 1 to 2, 2 to 4, 3 to 6. It's doubling. So what's a hash function that could arise from this? H of x is equal to x mod 10 to get the ones place, and then times 2, right? That could get everything there. So zeros to zeros, that would get, so 21, that would get the 1, multiply by 2, end up in there. 31 and 1 would all go into index 2, right? What would be a better hash function? Literally anything else. I think a better hash function would probably be like just doing x is equal to, there's 20 slots, so mod 20 would work. Although the purist in me wants to do a prime number, so I would bop, but that would waste the slot. So that's why I like this question. All right. Let's see. Now, I really like this problem 7. Suppose we first insert an element x into a binary search tree that does not already contain x. Suppose then we immediately delete the x from the tree. Will the new tree be identical to the original one? Yes, give no more than 3 sentences. If no, give a counterexample. Draw pictures if you necessary. I didn't write the final exam, but it's fine. All right, so this one I like because technically either are right if you can, because it depends on the assumption you're working with. For our class's purpose, it's going to be yes, the same, and we'll see why. And I can draw pictures to show you why. For no, the no would be correct if your example of a binary search tree is a self-balancing binary search tree. Because a self-balancing binary search tree, once you insert something, you could rearrange. I suppose we need to also define identical as well. Identical means that it's got the same, again, I'm going to use identical to mean the same structure and the same items, okay? So if with a self-balancing binary search tree, you can add an item to a tree, it's now unbalanced, it now needs to rebalance itself, so everything moves around, and now you delete the item, and it ostensibly doesn't have to rebalance, you know. So there you go, binary search tree there. But for our actual example of what we've seen in our classes, right, the way that's going to work in practice is that we've got ourselves a tree, all right, whatever, and whenever we add a node, we're going to add it as a leaf. Okay, so we've just added our x. Now it says, suppose we immediately delete x. Deleting a leaf is no problem. We just simply replace it with null. So nothing in the tree changes. So it would be identical. Make sense? Great. Let's move on to another one. Okay, I like this one a lot, and then I'll move on to the Harvard one. I plan on going over at least, my plan is to go over 3 plus 1 question. Okay, All right. So over here, we've seen many different types of data structures, including the following. A list, either a linked list or array list. 2D arrays, technically are data structures, so are 1D arrays. A stack, a queue, a hash table, a tree, a binary search tree, undirected graph, a directed graph, and a directed acyclic graph, right? Which are all different graphs, but they're graphs. Right. For each of the following applications, indicate which of these data structures would be the most suitable and give a brief explanation for your choice. Okay, there might be something lost in translation in one of these, but that's okay, because again, cultural norms, I'm dealing with all right, so this is from Washington, so this is making a lot of Washington references. I'm not talking about Washington, D.C., I'm talking about Washington, the state on the west coast of the United States, so the one that's much closer. The map of the Puget Sound highway system is used to display traffic times on a web page. The map displays principal cities, intersections, and major landmarks, the roads that connect them, and the travel times along those roads. Okay, the travel times between them along the roads. Travel times along the same road may be different in different directions. So what data structure would you use to capture this? A map, something like Google Maps. What would you use to capture as a data structure? Because we have principal cities, intersections, major landmarks. We have the roads that connect them and the travel times. Graph. Specifically, we'd be looking at a directed graph, right? And so now it also asks if we say it's a graph, what are the vertices and edges, and what are the weights? So vertices and edges, it's a directed graph because, again, travel times along the same road may be different in different directions. So the edges and weights, so the edges are saying there's a direct connection between the two, and the weight is just simply your travel time, and your locations are your locations, the places to travel to are your nodes. This is actually very standard this is actually the classical representation of graphs in a lot of texts. And prior to social networks was the easiest way to explain graphs. Now that we have social networks, it's a lot easier to explain graphs in their most abstract form, which is relationships. Okay, 8x8 board for chess. Each square can be empty or contains a piece. What did you use for your chessboards? What data structure do you use for your chessboards in your Sudoku, in your 8 queens in Sudoku? What did you use to represent your? Yeah, we used arrays. We used a 2D array. That was one of the choices, by the way. Okay. Okay, Boeing is one of the big aircraft manufacturers. If you're a U.S. citizen or working in the U.S. with a green card, working for Boeing is one of the ways to get big money because they also contract with the military and other government projects. Okay, a computer model showing the dependencies between steps needed to assemble a B-787 airplane at Boeing's Everett plant. Okay, now believe it or not, this is also a graph. This is specifically a directed acyclic graph because it's all about dependencies. When you see the word dependencies, that means it's a directed acyclic graph almost certainly, because that means we need to complete this step, and we have to complete these 2 steps before we can do this step. Right? Makes sense? Now the issue, and it's going to be directed acyclic because if we don't specify that it's acyclic, then you could have a situation like this, and that makes no sense because that means you have to complete, like we'd have to complete A before B, but then you have to also complete B before A, and this gets Kafkaesque, referring to Franz Kafka. I don't know if that's part of your literature, but it is in American classes, Kafka. Okay, now I don't know, does everybody know Scrabble or no? Okay, is everybody familiar with the game? This is one of the cultural things, right? Scrabble is is a game. Again, it's a big game in the U.S. or fairly big. It is a board game with English words where basically you are dealt a hand of word. So you dealt a hand of letters and you try to build letters on a board. And one of the main difficulties of Scrabble is thinking of these valid English words, right? You can't just put completely random words. So a list of legal words. So what would you use to represent a list of legal words in a Scrabble game? We want to be able to quickly check whether the words used by the players do in fact exist in the list. So we want to be able to check, is it a legal word? Now, now, even though it is the wrong answer, I would have to count it correct if you mentioned list, because I said a list of words, right? You asked for a list, I'm going to store it in a list, even though technically it's not the best answer because it's not the fastest. The fastest data structure that's applicable here is a hash set, so technically a hash table here, because hash sets are great. It either exists in the list or it doesn't, and you check that in constant time. Description of inheritance relationships between classes and interfaces. You could describe that as a directed acyclic graph because, I mean, you might want to say, technically you would say, oh, it's a tree, and that would be true for classes. But for Java, you also have interfaces, and you can extend one class, but you can implement multiple interfaces. And now that you have multiple parents, you're in graph territory, right? Trees are graphs. So first off, so just to be clear, trees are graphs, but they're a special graph where if you have n nodes, you have n minus 1 edges, and so if you're in that situation, it's a tree, and also there's no cycles, and you only have one successor generally. Okay. The history list so this is one of those where I'd say it's ambiguous. You could argue either way. The history list recording sites visited by the user of a web browser. New sites are visited, they are added to the list. The list also supports the operation going back. So basically it's asking you to implement the forward and back buttons. What data structure should you use? And the data structure I would use, first off, is that, again, they use the word list over here. So you could use an array list for either, especially or a linked list to implement both. So you could go forward and back. Yep, you could also use, the other answer is to use a stack. And each button is its own stack. Right? So multiple answers here. All right. So this one, IntelliJ, I'll go ahead and post it up. So it says, here is your node. Notice that they didn't go over generics. They just simply used integers for their items that they were storing, which is perfectly fine. But I like to do that emphasis of generics since they're useful. So complete the definition of the breadth first search below to form a breadth first traversal of a binary tree and print the node data values in the order there. So it says, given a tree, do breadth first search on it. This is also known as level order traversal, and it's actually a lot easier than it looks. So I'm just going to go ahead and delete this. New exam review. I'm going to create a node, public static node E takes in an E. I need to do that. No, public static E item. Oh, public static class, right? I have to say class. E item, node E left, node E right. Okay? So we've got these. Now, what are we going to do? We are going to do, we want to do breadth first search traversal, so public static E, let's just do, we'll use a list as our output. A list, public static E, list E, BFS, alt enter, and we take in a node E root. Okay. And technically it would be comparables, but that would make the line extra long. So it doesn't matter for this case though. List E visit order. Now with normal BFS, I would have to keep track of when I visited, have I seen this item before? But because I know it's a tree, and I know that I'm not going to have any back edges, in other words, edges that basically make me do a cycle, I know that every edge that every node I visit is going to be a new unvisited node. So what I need here actually is a Q. Now remember, the way to pronounce this word is to say the first letter and then not say any of the others. Because English is funny like that. I know that Japanese is technically hard, but at least you don't have to deal with ambiguous pronunciations. Right? If I see a character, I know how it's going to be pronounced. I suppose it's more difficult for kanji, but you get what I'm saying. Okay, Q is equal to new, and then Q is an interface, so I'm just going to use a linked list to implement that interface. If you put in Q is equal to new Q on an exam, I'm not going to care. But because all that matters is the operations here. We're going to put the Q. It should always be NQ, but they like to use offer as the way to add something to a queue in Java. I have no idea why they do that. Oh, okay. Oh, right. It's a queue of node E's, right? And yeah. So visit order. Technically, I guess I should say it's a list of node E's, and I'm going to return a list of node of E's, whatever. It's just going to add the nodes directly that I return, as opposed to the items. Return visit order. So, while q.isEmpty is false. While we still have stuff in the queue, that means we still have stuff to visit and process. So then I'll say I will say node E current is equal to q.poll. Q.poll is how we get the top thing out of the queue. Visit order.add current. If we cared about the items, it would be current.item instead. And then finally, what we have to do is we have to add its children in, okay? Which is that we are going to say current, so q dot offer my current dot left q dot offer current dot right. Okay, now the only thing we have to worry about now is the fact that left and right can be null, right? So we have to deal with that somewhere, right? We can either deal with it over here. When we offer something to the queue, we can add, before we add it to the queue, we can do an if statement saying, hey, if current.left is null, don't add it. That's one way to do it. Other way to deal with it, since I don't want to bother writing two if statements, is that we can say, hey, current is equal to q.poll if current equals null, sorry, if current is not equal to null, right, we'll just do that. So we'll do this only if current is not equal to null. And so, yes, we will be adding nulls into our list, but as soon as we identify them, we just don't do anything with them, right? So just have to handle your nulls to get full credit. Okay. All right. So here's an adjacency list. This is a good one. With a representation of a directed graph where there are no weights assigned to the edges. Okay. So draw a picture of the directed graph above. Okay. So A, B, C, D. Okay. So A, B, C, and D. Okay. So when we see a list like a list like this, it is A. It's not A, then a B. We know that there's an edge from A to B, but this doesn't mean there's an edge from B to C and C to D. This means A is connected to B, C, and D. That's what the adjacency list says. It says these are the edges. These are who I'm connected to. A to B, A to D, A to C. It's connected to all those. Now it says we've got an edge connected from B to A. This is perfectly legal, right? You can have one edge going one way. You can have an edge from A to B and B to A if it's directed. And they did mention it was directed. So, okay, C to B, C to D, and then D doesn't go anywhere else. Okay? Another way to represent this is an adjacency matrix. Draw the adjacency matrix. I think technically we'd write it. I'm going to go ahead and just simply create the adjacency matrix over here. We've got A, B, C, D. A, B, C, D as my adjacency matrix. Now there's different ways to represent this, but in general, the way that we do this is by saying if we don't care about, if there's no weights in the graph, we just use ones and zeros. 1 indicates an edge, 0 indicates no edge. If, on the other hand, there are weights, obviously we can use there's a few different ways to do that. If you're just kind of just being boring and using doubles as your weights, you can just simply say, if it's put in the actual value, but you can't use 0 anymore to say there's no edge. Instead, what you'd use is probably something like positive infinity, right? Yeah, you can go from A to B. It just costs you an infinite amount of cost, right? So another way you could do that is, have edge objects and then have nulls. But for simplicity's sake, it's ones and zeros. So first off, A, B, C, D. Nobody has an edge to themselves. That is actually something you can technically do, but because nobody has an edge to themselves, no worries there. Now we'll just go row by row. A is connected to B, C, and D. 1, 1, 1. B is connected to A. 1, and then nothing else. C is connected to B and D. C, B, and D. And then D is connected to nobody else. Right? With directed edges, it's super easy because you just read them out. For undirected, you would have to make sure that it's reflexive. Right? If A goes to B, B goes to A. So it would be mirrored along this central axis. Central diagonal. Okay. This one's a decent Dijkstra's algorithm rundown. Now it is computer science unwritten law that anytime we go over Dijkstra's algorithms in a class, we gotta do it in your final exam or in an exam. The 3 students in 3223 this semester, they did Dijkstra's algorithm in the previous semester in 2168. They're still going to do Dijkstra's this year because they need to know. course, the difference is I'll be asking them about why Dijkstra's has certain the runtime it does. Okay? So over here also is just like from a pedagogical point of view, this is something I hate. We have these edges which use numbers, and we have these nodes which use numbers. That's a no-no in my book. So we're going to go ahead and relabel these things as A, B, C, D, E, and F. I know those are terrible looking, but honestly not much worse than my normal handwriting. Okay, but the idea here is now that we've got over here A, B, C, D, E, and F. Okay? So now we can have a much easier time going through our graph. Okay? So we want to use Dijkstra's algorithm to figure out the shortest path from vertex A to all the other vertices. Update the edges, the entries in the following table. So again, what Dijkstra figures out is the shortest distance from A to not just a target node, but from A to anything else. And that's what we care about. Okay? So A to everything else. Update the entries in the following table to indicate the current shortest node distance and the predecessor. So that's how it figures it out. It keeps track of your distance and it keeps track of your predecessor. The distance is the distance from A to that vertex. Here it's A. And the predecessor is the node that basically the beginning of the edge you just came from. So initially, everybody starts out as A, your starting node is 0, and everything else is infinity. And then your predecessor you can either put A or nothing for A, and then you have nothing as your predecessor for everything else. So the way it works is you can either initialize it, but why bother? I'm going to do it the same way as everything else, which is I look in the distance for the node with the cheapest distance, the closest node. That would be A. So we're going to remove A from our consideration, and now we look at the values coming from A. Sorry, the edges going out of A. From A to B, we have A to B, is A to B is 2. Is 2 plus 0, the cost to get to A, cheaper than infinity? Yes, it is. So what we'll do is we will remove that, and we'll put down 2, and we'll say we can get to B with a cost of 2 from A. I mean, we can skip this step and just put down 2 and 2 and 3 for C, but honestly, I like doing it like this so that we have the practice. A. Now we look at our other vertices, A to C. Is 0 plus 3, the cost to get to C, so the 0 plus 3, the cost to get to A plus the cost to get to C, is that cheaper than infinity? Yes, it is. It's cheaper than our currently known cost. So we replace that. Those are the only ones we know. So now we have B and C. A is out of consideration. So now what we go is we look at our table and we say which is the cheapest cost? 2, 3, infinity, infinity, infinity. 2 is the cheapest. So now we look at 2's edges. The cost to get, B has 2 edges, 3 and 5. So now we ask ourselves, is the cost to get to get to B plus the cost to get to E, so 2 plus 3, 2 plus 3 to get to E, is that cheaper than the known cost for E, which is infinity? Yes, it is. So we put down 5 for E. We put down B over here. Make sense? Because we can get to E we can go from A to E for a cost of 5, and we're going to just have to pass through B to do so. That is what this is saying. Okay. And now B to D, same deal. Costs 2 to get to B, 5 to get to D from B to D. So that's 2 plus 5, which is 7. Down 7 there. And B. Okay, as well. Now we look at this. We've got 3, 7, 5, and infinity. 3 is the cheapest, so we're going to select that. So C has only one edge coming out of it. And the cost, and that's to get to D, which we already know the cost of, but it's not one we've eliminated from our thoughts. Okay, C to D. So A to C, the cost to get to C is 3. We know that from our table. The cost to get to D is 1 from C. So 3 plus 1, is that cheaper than what we already know? Yes, it is. It's cheaper than 7. 4 is cheaper than 7. So we cross that out, put in 4 over here, and go through C. We can get to D through C from A for a cost of 4. Now we look at this, and it just so happens that we're going through them in alphabetical order, right? D is the next cheapest node because it has 4. It has one edge we care about, which gives us a cost of 2. It costs 4 to get to D. 2 more gives us 6 from D. So, and the way this works is now we can say, okay, so what is the path to F? The path to F is you go through D, you have to go to D to get to F. To get to D, you have to go to C. To get to C, you have to start at A. That's how the predecessor kind of thing works. That's why we care about it. Okay, and that gives us 6. And now E is 5. Sorry, E is the next one. So what do we get here? E has a cost of 5 to get to it, plus 4. That's 9. Is 9 cheaper than 6? No, it is not, so we don't use that. We go to F. F has nothing, no edges leading out of it. We're done with all of our nodes. So the list in which everything was processed, it was A, B, C, D, E, F. You gotta understand, your professors are just as lazy as you are. We're all human, so we're all super lazy. This is why in math tests, so often your answers are 1, 1/2, -1/2, -1, or 0, because your professor is lazy and they want something easy to check. This is also why this is true for physics as well. The number of times your answers come out to one of those things is very often. Okay, start from that answer and work backwards, and it becomes for them, and it becomes a lot easier to write the question. Similarly, I'm the type of guy who has in his freshman class given true-false questions where all the answers were true. Which, if you think about it, it was a series of 5 questions, so there was a 1 in 32 chance that was an outcome. And you've probably had plenty of true-false. All right, if V is the number of vertices in a directed graph and E is the number of edges, what is the running time of the algorithm in big O notation? So we have to go over, so this one's actually pretty interesting. We have to go over every node and every edge, right? So is it V plus E? Right? Well, not really, actually, because and the answer is actually it depends on what we are using. If we're doing it the way Dijkstra wrote it initially, it runs in V squared because what we have to do is that this part where we have to go over all the edges, that's true. 100% true, we have to go over all the edges. But this part, we don't just go over all of the vertices. What we do is that we check for the cheapest vertice here, then we check the next cheapest then we check for V minus 1, then V minus 2, then V minus 3, then V minus 4 vertices. Dijkstra's original implementation is v squared plus e, where v squared is because it takes O of v squared time to go for all the edges, keep choosing the cheapest for all the vertices, keep choosing the one that is the cheapest to get to. Now this reduces, so this becomes O of v squared y. Because in the worst case, in a dense graph, E, the maximum number of edges is v squared. Okay? Now, we typically keep them separate, but since we're already at v squared, we might as well write it as v squared. However, if you use a minimum priority queue, if you use a heap, in other words, it becomes E plus v log v. And here it's using a Fibonacci heap to do that. So let's see, where is the priority queue? Yep, E v log v. For sparse graphs, would be good. If you use a priority queue, then it becomes E plus v log v, because you're just basically, this log v becomes a lot easier to handle. Because, that extra v you got over here from changing becomes log v because of how often you're processing it. Also, the other issue is that basically that it does cost to have to reshift everything in the array, in the heap, as you update it, but that's why the Fibonacci heap gets down to a awesome runtime. But regardless, the implementation matters here. So let's see. Two of the most common divide and conquer sorting algorithms are quicksort and merge sort. In practice, quicksort is used for data in main storage rather than merge sort. What is main storage? That's just a fancy way of writing RAM. Quicksort is used for sorting data in main storage rather than merge sort. Give a reason why quicksort is likely to be the preferred sorting algorithm over merge sort. Because, as we discussed, quicksort uses basically log n space, and that space is is very cheap because it's just the recursive frames that you have to keep track of, right? It's the recursion. Whereas merge sort always requires O of n space to do. It's much more space efficient. Okay. Worst case, so now here's another important one. Quicksort's worst case runtime is O of n squared, but it has an expected runtime, its average case, is n log n. And that's true if the partition function works well. What needs to be true about the partition function in order for us to get n log n? That's the first part of this. So what has to be true about partition in order for us to get their n log n function rather than O of n squared? So let's think about that in reverse. What has to be true for us to get an O of n squared runtime for quicksort? To get an O of n squared time for quicksort, what we would have to do is to choose a bad partition function every single time. So let's assume that quicksort is given a fully sorted list to begin with. Right? So, and then let's all assume that we always choose the leftmost item as our pivot. That's our strategy. So now we choose the leftmost item as our pivot, and we've got 2, 3, 4, 5, 6. So basically, everything is now is on the bigger than side. Then simple. So each recursive step, we're only reducing it by 1. So rather than our runtime looking like this, T of n is equal to 2 of n over 2, sorry, rather than our t of n being, let's see if I got this off the top of my head correctly, rather than it being 2t of n over 2, so rather than being two problems of size that, plus n time over here for each layer, right? To recombine all the work, it takes n time. Rather than that, it becomes t of n is equal to t of n minus 1 plus n, which means that we're reducing it, rather than reducing it into two problems of half the size, we're taking the problem and reducing it into a single problem of one less. And then we're spending n time on it. That, if you think about it for a second, that kind of unfurls into n plus n plus n plus n plus n plus n, right? This unfurls into n plus n minus 1 plus n minus 2 plus n minus 3 plus n minus 4 plus and so on and so forth. So yeah, that becomes n squared. And this unfurls, as you'll learn, into n log n. So what happens? So what has to be true about the partition function for n log n? We need half the items to go to the left, half the items to go to the right, about half, right? Which means we need this to be close to the median. And by close to the median, I need it to be between the 25% and 75% percentile, if that makes sense, right? You know, and that will ensure that basically on average, everything gets divided by half. So I need it to be, basically I need it to be close to the pivot to be close to the median. In practice, how do you assure this happens? There's a few different algorithms you can use to select the median, but a cheap and dirty way is like choose, if I've got my array that I'm if I've got my array or subarray that I'm quick sorting, here I choose the beginning item, the item directly in the middle of the array, not the median, but just directly in the middle, and the ending item. And I sort them, and I figure out which of those is the middle, and I move that to the beginning. That makes sense? I move that one to the beginning. Doesn't take much extra time, and it ensures that there's going to be. It helps make it less likely that I'm going to get a bad pick, right? If you think about it from the sorted item perspective, if I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Suddenly this means that if I do that, that's going to ensure that 5 becomes the pivot, and now we get back into a clean quicksort. It helps. Okay. Let's see, this one is... So now, let's see what else we have. Eulerian path, which is not something we went over. So let me go ahead and look up Harvard practice final data structures. They normally have a very good one. Do we need to take a break beforehand? Okay. Let's take a brief break. I'm going to just make sure this is the correct one. Yes, it is the correct one. Okay. So, okay, I'm going to try to go through this as quickly as possible because it seems wise. All right. So suppose that items A, B, C, D, E are pushed in that order onto an initially empty stack. A, B, C, D, and E on a stack that's initially empty. If two items are then S is then popped 4 times. As each item is popped off, it is inserted into an initially empty queue. E, D, C, B. If 2 items are then removed from the queue, what is the next item that would be removed from the queue? And the answer is C, right? Remember, first in, last out, first in, first out. If the binary tree below is printed in pre-order, what would the result be? Well, let's do it ourselves. Pre-order means that we would start, is that process myself, process my left tree, process my right tree. So it's not A and B. So 6, then I would go to my left, which is 17. And 17 says, now that I process myself, process my left tree, then my right tree. I'm done processing myself. So done processing both my trees, so go back to 6. 6 then says we're going to do the my right subtree, which means I'll do 22 next. And then there'll be 16 and then 12. All right. I like this one a lot. A graph implementation that uses a 2D array to represent the edges would be the most reasonable in which of the following cases? Some amount of nodes versus some amount of edges. I'll go over that in just a second. And the answer is, or E, none of these, because it can only, a graph can only be represented by a linked structure. This is incorrect. You can represent a graph as with a 2D array. We call that an adjacency matrix. Okay, the question is, where do we use a matrix? Where do we use a adjacency list versus matrix? And it depends on whether it's sparse or it's a dense graph. And how do we define dense? Dense means approximately 25% of all possible edges exist. In other words, the number of vertices, the number of edges divided by v squared is greater than or equal to 0.25. Make sense? 25% of the possible edges exist. Okay, if we've got 1,000 nodes, that means that we've got 1 million possible edges. 1,200 edges. 1,200 edges, 1,200 is only 0.1% of the possible ones. Ain't A. 100 nodes, 4,000 edges. I like the odds a bit better here. That is 10K. No, so we've got 4,000 nodes, edges over 10,000, which simplifies to 4 out of 10, 40% of all possible ones. That's probably the right answer, but we'll continue on. 1,000 nodes, which is 1 million possible edges, versus 10,000 edges, that's 1%. So not really. So again, not this one. 10 nodes, 20 edges, which using some simple math, that's 100 possible edges, right? So 20 out of 100, which is 20%. We're getting better, but it ain't the 40% usage of possible edges that B has. So the answer for this one is B. A binary tree is constructed of nodes that are instances of the following class. We've got, binary tree, just standard binary tree node. All right. Consider the following method. Mystery takes in a root, and what does it say? It says that if root.right is equal to null, if I've got nothing to the right, return myself. Otherwise, call mystery on root.right. Make sense? So call mystery on my right side. So we're going to keep calling mystery on. So we're going to start at the top and keep calling the right side until there's nothing left. right? That's what it comes down to. So you consult 3 supposedly tech-savvy consultants. You get the following 3 opinions about what the method does when you give it the root of a tree. Consultant 1 says last node in order traversal, post-order traversal, and level order traversal. Make sense? So the first guy says, oh, it's the last node in it that you do if you did an in-order traversal. Second guy says post-order. Third guy says level order. Which of these opinions is correct, regardless of what, no matter what the tree looks like? So let's look at each opinion. Opinion 1 is definitely correct. Why is that? Because the last node of an in-order traversal is always the biggest node in the tree, right? It's always the node with the biggest item. And the biggest item is all the way to the right. So if we start at the beginning, we're going to keep going right and right and right. And it's always going to be the biggest item, because if we had to go left, that would be less than something. And the biggest item can't be less than something, right? So this one is correct no matter what. Okay. Last node visited in a post order. Post order always means process my left tree, process my right tree, process myself. That means the last node that means the post order always returns, the last node in the post order is always the root. So consultant 2 is only ever correct, if basically if we have no right subtree. So he'd only be correct in this case, where we have nothing, right? All right. So consultant 2 is wrong. Now, finally, let's go ahead and look at consultant 3. The last node in a level order traversal. Level order is just simply the fancy way of saying breadth first search. And at the first glance, and I initially answered this wrong, that you'd think, okay, yeah, he's correct. It's going to return this item as well. But I mean, if you delete that last item and make it a complete tree, it's still complete, then is that still going to be correct? I mean, this would be the biggest node in the tree and the last item in a in-order traversal, but the last item in a level order traversal would be this. And so consultant 3 would say this item gets returned, and that's less than something. It isn't the biggest node in the tree. It's not this one. So consultant 2 and 3 are both wrong. So the only answer is A. Okay. Question 5. With the poorly chosen hash function, it is possible to have a situation in which the search time in a hash table of n items goes to what runtime? So first off, what do we want in a hash table? We want this, so obviously that is wrong. So obviously that's wrong. That can't be the worst case runtime. N factorial seems a bit weird because a hash function, I mean, you could make some kind of data structure that, like, the search time is O of n factorial. But I suppose, but that's not particularly useful for us. And also, like, the hash function doesn't do anything to the table itself. You'd have to change the table in order to do that. Or rather, and a hash function, all that does is says, given a key, give me an index, essentially. That's essentially, I'm simplifying a bit here, because technically, a hash function is technically its own thing, but for the purposes of a hash table, it gives you an index. Okay. So, so it's not this, right? So let's look at a poorly chosen hash function. Just h of x, give me x is equal to 0. That is a poorly chosen hash function. Okay, that's about as bad as it can get. It maps everything to the same spot. If everything's mapped to the same spot, then the search time for a single item would take O of n time, because we'd have to start at the beginning and look through all the possible collisions that have happened. So A is the worst. O of n squared is only true if you have to do that for like n items, not just one. We did this in the first for the first exam. No need to do it again. A police department wants to maintain a database of up to 1,800 license plates of people who receive frequent tickets, so it can be determined very quickly whether or not a given license plate is in the database. So we're keeping a database of these 1,800 people who frequently get tickets. Speed of response is important. Efficient use of memory is also important, but not as important as the speed of response. So basically, we want something with the best runtime, but if we have to break a tie, we'll break it by space. Okay, which of the following data structures is the most appropriate for this use case? A sorted linked list. To find something in a sorted linked list, you'd have to go to the middle, which means you have to iterate to the middle, which takes O of n over 2 time. Then you'd have to go to the the middle of the next part, which takes n over 4, then n over 8 time. I feel like Zeno and his paradox here. To get anywhere, you have to go halfway first, and because you have to keep going halfway to things, you never get anywhere. That's his paradox. But anyway, point being is that seems like a terrible idea. No. In fact, or if we were going to do binary search like that, that's how it would work. So instead, the only way we can look for an item in a sorted linked list is linearly by going up through stuff. It takes O of n time to look for something. We can do better we know better search algorithms than O of n. A sorted array with 1,800 entries. That's about as space efficient as it gets because you have 1,800 items, 1,800 spaces. No extra space used. No overhead like you would have in a linked list. And the runtime is better. For a sorted array, you can actually do a functional and working binary search. Now, all of these are hash tables, but not all hash tables are built equally. Open a hash table using open addressing using 1,800 entries, 3,600 entries, and 10,000 entries. Now, Knuth had a formula. Expected lookup. Okay, here we go. With linear probing, which is what we're assuming here. Let's see, where did you, Knuth? Right? There we go. The expected cost of finding something in this table is 1 plus 1 minus alpha inverse. So that's, in other words, the cost is going to be, so the cost of doing this, of finding something, the expected lookup time is 1 minus 1 over 1 minus alpha. What is alpha? Alpha is the load factor, okay? Alpha is the load factor. In other words, how much this is filled up. In other words, if you have n entries and it's filled up by k amount, right? It's k over n. We're actually, let's not use n because n is the number of items we've inserted. C over n. Now notice that n is no longer involved in the equation. Doesn't matter how many items we've well, technically be it out over t. But what we can see here is that really depend on how many items are already in there. The capacity is something we always set, but this load factor is always something we select. We always say there's a max load factor. It's never going to get bigger than a certain amount. Like for most hash tables, we might say it never is bigger than this amount. We're going to enforce it's never bigger than this amount. This is how we get around the whole idea of of it constant of it being, you know, a constant time. Sorry, this is how we make sure it's a constant time and get around it being like linear or something. We don't have n involved anywhere in this equation. So what does that mean in practice? Okay, well, let's calculate. The first one was 1,800. We have 1,800 entries and we have 1,800 slots. So that would be that would be this. That seems like that's 1 over 1 minus 1, which would be that's, you know, undefined. Not, you know, legal operation can't divide by 0. So let's go ahead and change it up for a bit. Now, what am I actually talking about? The comparison I like to use is that it's a lot like a parking deck. Okay? If you've ever parked a car on a parking deck, you know that if the parking deck is full, right, then it takes forever to find an empty parking spot. But if it's like half filled, no time at all to find anything. And the collisions are a lot like that. So we're saying if this thing is almost completely full, let's go ahead and do the we're going to need our calculator for this one. We won't need it for the other ones, but we definitely need it for 1799 out of 1800. It says I'm in programmer mode, so of course it's not going to give me the real answer. 1799 out of 1800. 0.99. We're going to just call that 0.999, which means that this is going to be. 1 minus 1 over 1 minus 0.99, which is going to be equal to 0.001, which is 10, which is 1 minus 1. Oh, sorry, this should be a plus, not minus, plus. Oh, I have a plus there. Plus 1 over 1,000, which that just flips and becomes this, which means in total it takes 1,001 average lookups on average if we implement it like that. That does not seem efficient at all. Okay, that's almost as bad as O of n. Almost as bad. Sorry, almost as bad as, well, actually, it's technically, I mean, it might be even worse because it's more than half n over 2, and, you know, you'd at least expect to find half of them. Okay, regardless, what about something more reasonable? What about the other two? 1 plus 1 over 1 minus, it was, right, 900 out of 8, sorry, we had 3,600 entries, so 1,800 out of 3,600. Okay. That was the second one, hash table 3,600. That reduces to 18 over 36, which is 1 over 2. This becomes 1 plus 1 over 2. Sorry, 1 divided by 1 over 2, which reduces to 2. Right? 1 over a fraction, just flip the fraction. And so it becomes 1 plus 2, so that takes on expected 3 steps to find. Okay, and now for the final one, 10,000 entries. Okay, 10,000 entries. Give me a second. I'm actually going to make the math a bit easier for us. 1 plus, now we can do 10,000. 1 over 1 minus 1,800 over 10,000, right? 18 over 100, that becomes 9 out of 50, which is, just coming down to the same thing, it doesn't matter, but 9 over 100, which is, so this would be, once we do subtraction, right, it becomes 0.82, so 82 over 100. Flip that around, it becomes 100 over 82, which is let's just call it approximately 2, right? Approximately 2. Right, everybody kind of followed? So it goes, so between these ones, you've got something that's 3 and then just a bit slightly more than 2, right? Now, but they're both technically constant time. And this one uses a lot less space, right? Here we have to use twice as much. Here we've got something as fast as possible, constant time. We have to though use twice as much space as we would normally use to do it. Okay, which is a valid Huffman tree? Not this, because Huffman trees only have nodes values in it only has values on the leaves. Okay, now it says the E is the most frequent character, and then I as the next highest. It says 1, 2, 3, or none of these. So if E is the most frequent character, then we'd expect it to have the least distance from the root of anything, or be tied for least different distance. And here E is at the bottom, the most distance. Frequent characters have less code. Sorry, have a shorter sequence. So not that one. So is it possible for B? Well, it says that which of these could be a Huffman tree? So could be this one. Okay. And what this would need to be is that you've got, for this to, and all we have to find is one example where this could be true. And I think I've got it, where basically we've got, well, ideally what we've got over here is that we've got these guys, maybe they add up to 2. Let's go with them. Maybe they add up to 3. Maybe this adds up to, let's see. Maybe it adds up to 5. Maybe these add up to 6. I'm not sure how it would add up. The issue is, hold on a second.
But it should be I in place of T, right?
It depends. It's supposed to be the next most frequent. So
0, 0, 0, and
so it could be like 1 and 1 for these guys. They add up to 2. And now these guys have to come next. The 2, whatever these add up to, they have to go after this. Make sense? So it could be something like, let's go ahead and say 4 and 4. That adds up to 8, okay? 8 is, so let's say these are both 5 and 6. Yep, that works. 5 over here, 6 over here. This adds up to 11. Okay? And then 5 and 6. That adds up to 11. E is 12. So we would do 8 and 11. So we would add these two things together. They would have a combined weight of 19, and they'd end up on the right that way. So yes, it works. My initial instinct was it works. I just had to construct an example to prove that it works. Where basically you've got 4, 4, 5, 6. That works. Here's an example. And then 12. Basically for this to work, these all have to be kind of the same order of magnitude. They have to have the same approximate one, with I having the absolute most, and then E being heavier than most, having a higher weight than most of them, but not as it has a higher frequency than most of these guys, but is not as frequent as all of them combined. Okay. An array of 7 integers is being sorted by heap sort. After the initial phase of the algorithm, constructing the heap, which of the following is possible ordering Which of the following is a possible ordering of the array? Okay. 7 integers is being sorted by the heap sort. Remember, there's 2 phases to heap sort. The first is heapify, which is turn it into a heap. And the second part phase is sort, where we sort it. So it's talking about we're here in between the heapifying and the sorting. So in other words, it's been turned into a heap. Specifically, it gets turned into a max heap in order to do this. Sorry, I feel like I'm about to sneeze. So the first thing we have to do okay, is that we have to so what we have to do is basically ensure that these are valid max heaps. So the first item is the root node, and it's always, my twice of my index and twice of my index plus 1. So over here, 85 is bigger than 78 and 45. 78 is bigger than 51 and 53. 45 is unfortunately not bigger than either of its children, so this is not correct. Okay, what about 85? 49 is less than, 85 is the biggest in all of these, so we don't have to check 85. So 45 against 49 and 47, that's fine. 78 against 51 and 53, that's also fine. 78 against 45 and 47, 49 against 51 and 53. 49 is less than his children, so that's not good. And finally, let's double check the last one to make sure I didn't make a horrible mistake. 85, 51 versus 53 and 49. We've got a conflict right over here with 51 and 53, so the answer has to be B. Binary search tree was constructed by inserting a sequence of items into an initially empty tree. Which of the following sequences will not produce this binary tree? So let's look through this. So if we insert 5 first, that go to the root, then 3 would go here, then 9 would go here, then 4 would go here, 12, 7, 8, 6, and 20. This will make sense when we find the incorrect one. And I believe the incorrect one is the last one, so I'm just going to skip to that. 5, 9, 3, and now, so we've added 5, 9, and 3. Now if we add 6, 6 would go over here. It's greater than 5, less than 9. So and then if we add 7, 7 would go over here, and 8 would go over here. So it would not produce the same binary tree in the slightest. So that's what's going to, and the other ones, if you check it, it's going to be the same. Okay, blah, 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 don't need these. So you're going to be given something like this explicitly like this on the exam. Specifically something using linear programming. Okay. You're given an initially empty hash table of size 7 that uses open addressing. The following sequence of keys is to be inserted. Insert these keys using the following approaches. If an overflow occurs, say so and indicate the element that causes the overflow. So here we insert these keys into the slots, and each key goes into the index that is the key value mod 7. So for instance, to start off, 15 is going to go into 15 mod 7. What is 15 mod 7? That's 15 minus 14. That's 1. 17 is going to go into 17 mod 7, which is 10, 3, right? 17 minus 7 becomes 10. 10 minus 7 becomes 3, right? Also, it's 2 more than 17. 17 is 2 more than 15, so makes sense that it's 2 indexes up because that's the way modular arithmetic works. 8 mod 7, very easy for us to figure out, that is 1. So we're going to put it in slot 1, except, right, it's already taken. So linear probe, it says use linear probing to resolve this, which means look for the next available space, where next is defined as literally the next one. Just go up by 1. Oh, and look, we have an empty spot, so we're going to go ahead and take that. 23 is next. 23, the closest multiple of 7 is 21. 21, 22, 23. 23 would go here, but 8 just took that spot. So, next one, that spot's taken, so we go into here. 3 would go into here, 3 mod 7, right? These next two are easy, 3 and 5. 3 would go into 3, it can't, so it goes here, but it can't, so it goes here, into 5 spot, and 5 goes, I'm going to go into 5, except I can't. That spot's taken, so I'm going to go into 6. Now, what happens if I wanted to insert something like 4 in this case? Okay, what would happen? 4, I would try to insert here, I would try to insert here, and then do I crash? No. I go and look around. Okay? Now, in reality, you're never actually going to, you loop back around. In reality, you're never going to, fill it up quite like this. But suppose that now that this entire thing was empty. Sorry, we were doing stuff and we inserted, X, Y, and Z into here, and we wanted to insert something like over, and we wanted to insert A. A would just simply go to the next available spot. Right. Okay, it wraps around. In reality, it's never going to fill up, but we're not talking about reallocating here. We're just trying to do this. For now it says do the same thing, but quadratic programming. So quadratic probing. 15, 17, 8. 8 wants to go into this spot, but it can't, so it goes into the next available spot, which is 1 squared away, which is 1. Now, what we'll do is we'll go over this in a bit more detail with 8. With 23, we'll see how this works for 23. 23 wants to go into what spot? Wants to go into 21 plus 2, which wants to go to index 2. It wants to go here. So 23 wants to go here, but it can't. So it looks 1 squared away from its initial spot. But that doesn't work, right? Doesn't work because that's already taken. So it wants to go now 2 squares. So now rather than going 2 squares away from its initial spot, which is what you do for a linear, instead of going two indices away from its initial spot, which is what you do in linear, now we look 2 squared indices away. So too many squares. Okay, so the key here is that it's from its initial spot, which is 1, 2, 3 more, right? So for a grand total of 4, 1, 2, 3, 4, and now 23 happily ends up in here. 3 goes into here, but it has a conflict, so it goes over here, and then 5 just simply slots in. It's quadratic probing. Okay. And this one, it's not nearly as good for Dijkstra's, but I'll do it anyway. Okay. Sorry, I'm not good for Dijkstra's, but I will do the breadth first search and depth first search. Okay. And I say it's not good for Dijkstra's because it doesn't they never change. Once a value is established, it never changes. Okay. Perform a depth first search starting from C. I always like to start it from A, but they wanted to start it from C. Select the smallest edge first when appropriate. So if we're breaking a tie for depth first search, we do this. So for C, so we go with C, list the order in which they're visited in, which is important because you can do visit order or you can do post order, finish order. Right, so we'll start at C, 5, 22, 30. 5, we're going to select 5 because that's, the 5 edge because that's the lowest weight, so we go to B. B, we would select the 5 edge, but it would lead back to somewhere we've already been, so we don't select it. We've got 18, 20, 13, 17. 13 is the cheapest, so we go to A. A has 10, D is the cheapest, so we go to here. And normally you should probably be keeping track of how you got the places, right? So, because now at D we are at a dead end, so we need to backtrack to A, A has no good edges to go to. We backtrack. B has 2 more places it can go. Can't go here anymore. But 12 and 18 it can take, so it goes to F. F has nowhere to go to, so okay, and now B goes to E. Done with E, done with B, done with C. C bad phi. Okay. Now for breadth first search, that's easier. Still starting from C. Still starting from C. We start at C. And we say we want to visit, we start making a queue. Starts with C. C is out of the queue, and we want to go to, and we add C's neighbors. C goes to B, E, and F. B, E, and F. We add them in order by weights because it says to do the weights, the shortest weights first. So B, E, and F. So we're done with B. It's going to be the same order it goes into the queue is also going to be the same order as our output. So B, we add B's neighbors to the queue, which are at 13 and which are across 13 and across the 17 edge, so that's A and D. And now, honestly, there's nothing else to do except dequeue the queue because there's no other things to discover. So CB fad. Okay. All right, here it's asking you to rewrite the search so that it goes from iteration instead of using recursion. Not too useful. More useful is this problem, which is much easier if you use recursion. Hint, much easier if you use recursion. So what in the world is this method that we want to write? Because it's a good one. Okay, haven't done much coding, so I'm going to do this one in another coding example. Write a Java method named mir that takes a reference to the root of a binary tree and creates a new tree with its own nodes. That is a mirror image of the original tree. For example, if root is this node, then the return value of mirror root would be a reference to this node. And these are completely different new objects, okay? So, but the way it looks, right, is notice that you've got it was 1, 2, 3, 4, 5, 6, 7, and now it's 1, 3 on the left, 2 on the right, and then 2 has its own children mirrored. Instead of 4, 5, it's 5, 4, and then 5 has its own children mirrored. 6, 7. So while the children kind of swap where they are, the values that each child has doesn't change, right? 1 has 2, 3, 3, 2, but it doesn't have 4. It doesn't have 4 and 5, 4, 5, or 6 as children. This is one of those ones that is a lot easier than it appears to be, as is all with recursion. Again, sorry that this is taking so long, but I find that it is necessary to do this kind of review. Okay, node E, mirror node E. We're going to need an E there, and we're also going to need one more thing. We're going to need a constructor. Public node E item. This dot item equals item, just like that, right? Okay. So what we have to do here is we have to figure out, well, recursion always helps me to figure out what the base case is. First off, we got to make it stop compiling errors. Oh, right, return null. Okay, so we should totally think about what happens if root is null. So again, we think about our base cases. If root is null, what is an easily answerable question? That is very easy. If root is null, if the node unpassed is null, then the mirror image is just null, right? Right? Okay, what if I'm not null? Well, in that case, I need to create the node E, what we're going to call the mirror root, right? New, and it's going to be a new node. And what does it have? It has its own root.item, right? Same item as me, just a new node. And in the end of the day, I need to return this. And so now, what do I need to do? I need to create new nodes that are, my left child, new nodes that are left child for my left child and right child, and I kind of swap them. So, for instance, so I'm going to do this incorrectly at first, but on the way to a correct answer. So mirror root dot left is equal to a new, this is the incorrect part, new node, but it's on the way to correct answer. New node, root dot right dot item. And mirror node dot right, that should get a new node with my left item. But if we think about this, right, this leads into its own complications. What if my child is null, right? Then that's a null pointer exception right there, right? And also, it doesn't handle its own children, right? It doesn't handle my children's children, right? But if it's a recursive function, I should think about where to use this. Well, if I called mirror on one of my children, it would return, we've already established that mirror is going to return its own new node. So, what the correct answer is that I want to call mirror on my child, which will then create its own mirror nodes and handle swapping its own children, and I just need to swap my children. So, mirror.left is instead mirror root dot right So root dot left is equal to, well, it's going to be the clone of my right node. And mirror dot right is going to be the clone of my left node. And then we tell our children to create clones of and swap their own children. So surprisingly short, right? Again, recursive functions are very simple when you think about that. All right, 5 points. What is the runtime of your implementation of the mirror method? Use big O notation and explain your answer briefly. Very easy. It is data. They say use big O notation, so big O of n. Why? It's always going to be big O of n. The reason being is that we have, if you have n items, we need to make a clone. We have to make n clones. That takes O of n time. So for every item, we run mirror on it, which takes clone, which is a clone. Okay. Okay, so So the last question is one that I got a while back from another exam, and I really liked it. And but the exam no longer exists, but I remember the question perfectly. Suppose you have a log, a file, you know, and I'm going to skip the file reading part for us. Yeah, they don't need to. So suppose you have a log, a file that looks like this. It's formatted like this. Alice, some number, Bob, Alice, Bob, Carl, Alice, Dan, Bob, Ethan, Bob. And what is this? These represent username on the left and login time on the right. So we've got a file name that's full of usernames and their login times. Okay? Basically, Alice was logged in for this long, then she also logged in again for this long, and Bob logged in for these times. So what is our, and so our task today, the task of this question is find the average runtime, find each user's average login time, the login time for each session. So what we have to do is we need to count how many times each of them logged in, as well as what is the total login time for each of them, and then take their total login time divided by the number of sessions. That gives you their average. So we need maps, 2 maps. Okay, so public static void, public static, yep, we're going to just print out the answers. Public static void, logins, going to take in string file, we're going to just go ahead and read it, assume we have it, string file name, what we're going to do is we're going to say scanner is equal to new scanner, new file name, Alt enter. Come on, you know how to resolve this. Alt enter. Alt enter. And yes, now we know how to resolve this as well. Surround with try catch. Or you know what? I'm going to be even lazier. Add an exception there. Don't care. Just going to not even bother with the try catch. Okay. Now we need our maps. Map. We need. It's always going to be what we care about. Tracking is the user, and we need a couple of. We need to track the amount of times they logged in. Num logins equal to new hash map. We also need to keep track of the total amount of time they logged in. Time logins. New hash map. Now we could be fancy and like just keep it as one, or just make one map where it's a string to an array of ints. We're not going to be fancy. I'm just going to do two of these. Okay. So, and what I'm going to do over here to run this is I'm going to say wow scanner dot has next line. We're going to go ahead and say string line is equal to scanner dot next line. String fields is equal to line dot split on space, because we know it's going to be a space. It's a string array. Okay. We know that int. So we know that string name user is going to be equal to fields 0. I'm using more variables than I need to, but readability is king. Int time is equal, time is equal to, I'm just going to call t. Int t is equal to fields 1. Except that that's a string, so we're going to need to do integer dot parseInt right? Okay. And now what we do is we can say, so so we would normally do something like if num logins dot contains key, right? I'm going to be fancy though, and I'm going to say, let's see if I can use this appropriately. Nums login dot get or default, okay, key or integer, so the user. So this is the number of times they've logged in, okay? We're going to get the number of times that user has logged in, and get or default says if they haven't logged in yet, then I want a default value, which is going to be 0. So this gets me that number. So as a num, and then I'll say num logins dot put user. So I just did that in one line. I just split up what an operation that normally takes 2 lines into 1, but let's go ahead and do that in 1. Int prev logins is equal to that. I didn't finish writing it. I needed to add a +1. So num logins put user prev logins +1. There's also, I think, num logins dot put if absent, but I'm not going to use that. Also compute if absent, but again, no need to overcomplicate things. So int prev t is equal to time logins dot get or default 0 for that user. Again, what this does is just I don't have to do an if-else statement, right, to figure out whether or not it's been there. And we'll call this time logins previous t plus t. Right, this is the total amount of time. And that makes it a lot less lines than this normally is. Now that we've collected the amount of times everybody's logged in, we've collected the number of times the total amount of time everybody has been logged in for string user in prev logins dot keyset, not prev, num logins dot keyset, and we only need to iterate over one since they'll have the same keys, right? Make sense? Okay. So what we'll do is we will say user, so we'll get login int logins is equal to num logins dot get user, int time is equal to time logins dot get user, sout logins divided by, sout time divided by logins The only disadvantage here is that it's an integer divided by an integer. So we can fix that quite easily though by just doing 1.0 times, and that will convert time to a double, which will make sure that logins converts to a double. And that does it for that. Okay, I think that's 2.5, that's almost like an hour and 50 minutes of review. I think that's pretty good. And I went pretty fast for this one. I normally slow it down a bit, but today is the last day and I want to make sure I get to everything.